Welcome to Chapter 11, Support Vector Machines. In this chapter, we explore one of the most elegant ideas in classical machine learning, building it up step by step from concepts to Python practice and case studies. Support vector machines are supervised learning methods used mainly for classification, though they extend naturally to regression as well. In this chapter, we build the idea up from the ground. By the end of this chapter, you should be able to explain the basic idea of an SVM in plain language, describe what a separating hyperplane is and how it makes predictions, define the margin, and explain why the support vectors alone determine the boundary. You should also be able to distinguish hard margin from soft margin SVMs, explain the role of the regularization parameter C in the bias variance trade-off, and describe the kernel trick that lets SVMs draw curved boundaries using linear, polynomial, and radial basis function kernels. This figure captures the whole idea at a glance. The SVM finds the hyperplane, shown as the solid line, that maximizes the margin between the two classes. Only the support vectors, circled on the edges of the margin, determine where the boundary sits. At heart, an SVM is simply a method for drawing a boundary between two classes. The twist and the source of its power is in which surface it chooses. Here is the formal definition. A support vector machine is a supervised classifier that separates two classes with the boundary maximizing the margin, the perpendicular distance to the nearest training points of each class. Those nearest points are the support vectors, and they alone fix where the boundary lies. Before we can talk about the best boundary, we need a way to describe a boundary at all. In 2 dimensions, a line can be written with 2 weights and a bias, and in any number of dimensions, we collect the features into a vector and write the same idea compactly as W transpose X plus B equals 0. A separating hyperplane is one that successfully keeps the two classes apart. It computes a score from the features and predicts the class from the sign of that score. When the data is linearly separable, many such hyperplanes will do the job, each with 0 training errors. So, which hyperplane should we pick? The margin is the width of the empty corridor on either side of the boundary, measured to the closest training point in each class. The points that touch the edges of that corridor are the support vectors. Support vectors are the training points that lie on the edge of the margin, or, in the messier real-world case, inside the corridor. Here lies a property that sets SVMs apart from many other models. We have claimed that the SVM maximizes the margin, and that doing so amounts to making the weight vector small. To see why, let us fix the boundary as W transpose X plus B equals 0. A short derivation gives a clean result. The margin M equals 2 divided by the length of the weight vector W. So the corridor is exactly 2 over the length of W wide, with the boundary running down its center, a distance of 1 over the length of W from each edge. This figure shows how that margin width is derived. The support vectors lie on the dashed hyperplanes where the score equals plus or minus 1, with the decision boundary running midway between them and stepping across the corridor recovers the width. The cleanest version of the idea is the hard margin SVM, which insists that every training point be classified correctly and sit outside the margin. It minimizes 1/2 the squared length of W subject to that constraint, an objective that looks unintuitive at first but has a clean geometric meaning. Real data is rarely perfectly separable, so the soft margin SVM introduces slack, a small budget of permitted violations. It balances 2 goals: keep the margin wide and keep the violations few and small. A boundary too greedy for a wide margin will let too many points slip through. The knob that controls this balance is the regularization parameter C. A large C makes violations expensive, while a small c makes them cheap, tolerating some misclassified points for a wider, smoother margin. In the language of Chapter 5, this is just the bias variance trade-off wearing a new hat. What if no straight line can separate the classes? The kernel idea maps the original features into a higher dimensional space where a linear separator does exist, then finds the maximum margin hyperplane there. A kernel function is, in essence, just a measure of similarity between 2 points. We will work with 3 kernels throughout: the linear kernel, the polynomial kernel, and the radial basis function, or RBF kernel. Each kernel implies a different shape of decision boundary, yet all of them keep the maximum margin principle intact. The picture to keep in mind is 2 spaces side by side. This figure illustrates the kernel trick. Classes that are hopelessly intermixed in the original input space on the left become separable by a single linear hyperplane after the mapping into a higher dimensional feature space on the right. The linear kernel is simply the plain dot product of 2 feature vectors. This is the SVM with no nonlinear lifting at all, the straight boundary we started with. The polynomial kernel lets the boundary curve and bend. It raises the dot product plus a constant to a chosen power, where the constant controls the influence of lower order terms and the power sets the degree of the curve. The radial basis function kernel, almost always called the RBF kernel, is the most popular nonlinear choice and a sensible default when you do not know the shape of your data. It measures similarity that fades with distance. Nearby points score near 1, and the value decays towards 0 as points move apart. The RBF kernel has a tuning knob, gamma. A large gamma gives each point a very local reach, so the boundary wiggles tightly and can overfit, while a small gamma gives a broad reach and may underfit. Because C and gamma interact, they almost always need to be tuned together by grid search with cross-validation. Here is the key point. An SVM has 2 personalities. The linear kernel draws a flat boundary and excels on high-dimensional, sparse data like text, while the RBF kernel draws a flexible curved boundary but demands that you tune C and gamma together. Whatever the kernel, always scale your features first. Feature scaling is not optional for SVMs. We can standardize each feature to mean 0 and standard deviation 1, or normalize it into a fixed range such as 0 to 1. The cleanest way to apply scaling consistently to both sets is to wrap the scaler and the SVM together in a scikit-learn pipeline. The SVM machinery is built for 2 classes, so how do we handle more? 1 VS-REST trains 1 SVM per class against all the others, assigning a point to the highest scoring classifier. 1 VS1 trains 1 SVM per pair of classes and lets them vote. Happily, scikit-learn manages this for you automatically. SVMs occupy a distinctive niche, so it helps to know when they shine. They are effective in high-dimensional spaces even when features outnumber examples, strong on small to medium datasets, capable of nonlinear boundaries through kernels, and grounded in clear geometric intuition. They also have real limitations. Training scales poorly to very large datasets, where tree ensembles are often faster. Performance hinges on careful feature scaling. Choosing the kernel and tuning C and gamma takes effort. The models are less interpretable than logistic regression, and probability estimates require extra calibration. Even in an era dominated by deep learning and gradient-boosted trees, SVMs remain a valued classical tool, particularly for high-dimensional classification on modest amounts of data. Now let us put this into practice. Throughout the examples, we will work with the Breast Cancer Wisconsin dataset that ships with scikit-learn. This code loads the dataset, holds out 20% of it as a stratified test set, and then builds a pipeline that scales the features and fits a linear SVM, all in one tidy object that is trained in a single call. The pipeline standardizes every feature and then trains a linear SVM, which guarantees that the exact same scaling learned on the training data is reused on the test data. Moving to a nonlinear boundary is remarkably easy. Swapping the kernel is a one-line change. This code keeps the same pipeline structure but switches the classifier to an RBF kernel, then fits the model, predicts on the test set, and prints the accuracy and confusion matrix. The setting gamma equals scale is a sensible default that automatically adapts gamma to the variance of the features. Rather than guess at the best settings for C and gamma, we let cross-validation search a grid of values and report the best combination. This code uses grid search with five-fold cross-validation over a grid of C and gamma values, refits the best combination on the training data, and reports both the best cross-validation score and the resulting accuracy on the held-out test set. Let us see this in a real setting. A mid-sized software company receives thousands of support messages a day, each needing to reach the right team: billing, technical support, account management, or complaints. Sorting them by hand is slow and inconsistent, so they want a model that reads each message and routes it automatically. Text is where linear SVMs have long earned their keep. The recipe is to gather a few thousand labeled past messages, convert the text to TF-IDF features, train a linear SVM with the 1vs rest strategy, and evaluate per category, since a misrouted complaint costs more than a misrouted billing query. The workflow does not end at the first model. We read the misclassified messages, refine the pre-processing to handle typos, stop words, and product names, and retrain. The payoff is a classifier that is accurate, quick to train on a single machine, and cheap to run on every incoming ticket. The following code reproduces this ticket routing workflow using the 20 newsgroups corpus as a realistic stand-in for support messages. This code selects 4 newsgroup categories, loads the messages with headers and footers stripped away, splits them into training and test sets, and feeds them into a pipeline that turns the text into TF-IDF features and trains a linear SVM. Running this pipeline typically yields per-class F1 scores above 0.90, confirming that a linear SVM on TF-IDF features is a strong and efficient baseline for multi-category text routing. To summarize, support vector machines find the decision boundary that separates two classes with the widest possible margin, and when a straight boundary will not do, the kernel trick lifts the data into a higher dimensional space where a linear separator exists, without ever computing the new coordinates explicitly. If you would like to go deeper, 2 sources stand out: the original paper introducing the maximum margin classifier and a comprehensive treatment of kernel methods and SVMs in the context of pattern recognition. That brings us to the end of Chapter 11 on support vector machines, an elegant and enduring tool in the machine learning toolkit.